interest boxes you may find in the textbook, various chapters here and there. And they ask the question, does hot water freeze faster than cold water? So the thinking is, well, you put hot water in your freezer, because it's starting off at such a high temperature, it kind of gains momentum to get down to cold and freeze, compared to the cold water, which is really close and doesn't change temperature that much. That's the reason. Turns out you can argue either way, both yes and no. If you put hot water in your freezer without a cover on it, what's the hot water going to do first? Start to evaporate, which means you get less to freeze, and it will freeze quicker. But if you cover your hot water so it can't escape, then no. Because at a higher temperature, it's going to have to lose a lot more heat until it gets down to freezing compared to the cold water. Plus, putting anything hot in your freezer, hello, are you there? Plus, putting anything hot in your freezer, you're using extra electricity. You're making your freezer work harder to try to get temperature down. So you've had a meal, and a nice hot meal, you want to have some leftovers for sometime later. Don't immediately put it back into your freezer if it's still hot. Let it cool off from temperature first, then do it. Otherwise, you're making your freezer work too hard. Well, look how much it took to explain this. You got big experiments going on and so forth. So it's one of those trick questions you can actually argue either way. Meantime, we've gone through our section here on temperature, including the thermocline. We found out the thermocline was the decrease in temperature depth that we find in tropical water. Warm up at the surface, colder underneath. So there must be a big drop in temperature as we go down. So that thermocline prevents any vertical currents and mixing of nutrients from the bottom back up to the top, so we don't find as much life in the tropics as we do in cold polar waters. It's kind of a paradox. Reverse of what we find on land. You want to find lots of vegetation, animals, you know, in the tropics on land, not the case in the water. So as I mentioned last week, gross stories. Now ready. Pressure. What's pressure? As the molecules are moving around, they're going to hit each other, hit objects, hit the sides of the container, and how hard the impact is what we're going to call pressure. It's due to the collisions of molecules. As they hit things, including us suffering away, how hard the impact is what we're going to call pressure. Pressure increases with depth at 1 atm for every 33 feet down. ATM is not at your bank. What's ATM? Atmosphere. We've got 1 atmosphere of pressure exerted on us right here, and we're at sea level. You get down in the ocean just 33 feet deep, which is not very deep at all. You get to double the pressure in your body. You get down 66 feet, you get to triple the pressure in your body. So there's a huge, drastic increase in pressure with depth. Suppose you went to the bottom of the Mariana Trench. The increase in your pressure, the pressure on your body, would be over 1,000 times what we've got here at the sea level surface. We got about 15 pounds per square inch in our bodies, be 16,000 pounds per square inch down there. Because you get the weight of 7 miles of water pressing on you. So here we go. Why don't we feel that? Why don't we feel air pressure? Internal matches external. We get out in the ocean, we have to start to match the pressure. You've all seen these movies where somebody's got the deep sea diving suit on, they got this little metal helmet, a little door in the front they open up, and they're going around probably looking for treasure, doing something down there. Time to come back up, so they start pulling up on the hose, and there's no body. And they're scratching their heads. What happened to the person that was down there? Something scared them so much that they fled their suit that they couldn't survive. You have to have air. You wouldn't be able to match the pressure down there. So they take the little helmet and they open the little door in the front, and he's inside. all of them imploded. The only strong structure that was present, which was the helmet. A mass of flesh and bone and tissue all squeezed into the helmet. This is one of the extreme fears of deep sea diving, is that you don't match the pressure. You get down hundreds of feet deep, you've got to pump a lot of air down there to match the extreme pressure being exerted around you. And if you don't do it, it actually crushes the body. So I've checked with PhDs, I've checked with diving experts. This is one of the main fears about being down there really deep. And we'll have that addressed in our video. The only picture I've seen of this, I Googled it, I can't find any. The only picture I've seen is an old Time Life book. So if you clean out your garage, your attic sometime, you come across one of these Time Life books from back in the 1960s, there's a picture in there. And again, it's just a massive flesh. Like I said, so second story, let's reverse it. Space. You see movies where somebody's out in a spacecraft and they want to go outside the vessel, so what do? Put on the spacesuit, go in the airlock, take all the air out, open the door, go outside. Well, sometimes in these movies, somebody's forced through the airlock with no suit on. And they end up going out in space and they do this. Now, you put your body in outer space, what's going to happen to you? You're going to explode. Your blood's going to boil and you're going to blow apart. You're matching the pressure we've got down here. You go to outer space where there is no outside pressure and your body blows apart. The closest movie I've seen to this, James Bond, who else? License to Kill. He's down in the Keys, they got a hyperbaric chamber. What's that for? To slowly change the pressure. If you've been down really deep, you just don't come right to the surface. You got to come up very slowly, otherwise you get what's called the bends. They call it the bends because you do this. You're bent over in pain. What's happening? You're getting nitrogen bubbles inside your bloodstream. Very painful. It goes to your heart or your brain, you're done for. So you get to ease the pressure off. In the movie, it puts this guy in a hyperbaric chamber, set it to max. That's okay. Keep your mouth open, keep breathing. Then they took an axe and cut the hose, so all the pressure inside immediately went out. And it shows the guy's head get real big and he's bleeding from his eyes. So as I told you, it's gross. The whole key here in not feeling the pressure is inside has to match outside. You bring a deep sea fish up from the bottom, what happens to it? Blows apart because you mismatched the pressure on it. Down here, Harbor Ranch, which is in Fort Pierce, they put out these little styrofoam cups. They got them all labeled there with their names and designs and so forth. Prove it's theirs. The styrofoam cup has been smashed down to thimble size because of the pressure. There's no inside. There's no way to balance the pressure. It's just a cup. It's squeezed down to almost nothing. So one more time, how the deep sea fish survives the extreme pressure down there? Say it. For humans to do that, it's pretty tricky. You're better off in some kind of a steel suit or a steel deep sea. Question on pressure. All right, the third of our three key properties in dealing with matter is going to be density. Who knows the definition of density? What per what? We did that in Unit 1. Judge them. Mass per volume. In other words, how much stuff there is per space, how thick, how heavy, how compact something is. What we label here as density. We're going to look here at the spacing of the molecule. Take on that second term. Mass of water is fixed. We then look at the volume, how much space is taken up. Remember, matter is mostly empty space. We get down to the size of atoms and molecules. So we see how they're spaced apart. Fresh water was the defining point for density. compare all objects, once again back to water, just like we did on specific heat. And it comes out a nice even 1 gram per cubic centimeter is the density of fresh water. Gram again, cup your hand, a little bit of water in the palm of your hand, that's about 1 gram. Cubic centimeters, because volume is length times width times height. So you got 3 dimensions. Compare that to salt water. Did this in the last unit, more or less dense. It's going to be more dense, but it's subtle. You're only talking 1.03 because there's not that much salt in the ocean. It's only 3.5%, so it's a subtle change. However, let's suppose you're out at sea and you get a big rainstorm out there. Which one's going to be on top of the ocean, the fresh water or the salt? The fresh, because less dense and therefore it's going to stay on top. Again, people think if they're stranded at sea, they can drink the top of the ocean. You know there's a river nearby that's run into it. You just had a big rainstorm, a lot of fresh water coming from the sky. Oh, if you just drink the very top of the ocean, you're okay because it's fresh. Be very careful doing that. You've got to really know and understand what you're doing. Because again, your body cannot handle the salt content. It's subtle. When you're talking about 0.03 by density, the body can't handle it. Dehydrate. We've gone through that before. How about ice, more or less dense? Come on, ice does what? Float, so more or less dense. Yes, and it's considerable. We're down to 0.92. Ice, therefore, is going to float. The only solid that can float in its own liquid. Every other solid substance in the world is going to sink in its own liquid because the molecules pull together and they're more dense. In the case of water forming ice, the molecules actually spread apart and form a hexagonal shape. So, what's this? Okay. Frozen. Okay. You had a long day already. Where's the ice in the lake? It's on top because the ice floats. Why is that good that the ice forms on top instead of the bottom? Alright, life can survive. Life can get through a winter time because they've still got access to nutrients. If the ice was forming at the bottom first, that would cut the nutrients off. Life would have to regenerate every spring. But instead, because ice floats, we don't have to regenerate life every spring. It's going to preserve life through, it's still got access to nutrients. The water's going to be cold. You and I wouldn't like it, but the fish, shrimp, some plants can actually handle it. Secondly, what's the ice do to the water? Because it's on top, how's the ice acting compared to the water? Protective surface, what's it do? So it's your IN. What? Insulates. It's actually insulating the water. What did we say the coldest temperature was in the ocean? 28. Land can be 28 below. Or worse than that, even 70 below. The water never gets that cold because the ice is acting on an insulating surface. So 2 reasons. Ice floats in water. That helps preserve life through the winter time. And it also insulates, keeping water temperatures higher than what you see on land, much higher than what's seen on land. Once again, water is pretty special stuff, which I tried to convince you of. Any questions? Alright, now I got a couple of new terms coming, so I'll let you copy these down. Number 6, thermocline plus halocline is then going to be the pycnocline. Everybody say pycnocline.
Pycnocline.
Weird spelling there. Go ahead and copy those and we'll see what's going on. Alright, thermocline we did last Wednesday. Thermocline is the what? Decrease in temperature with depth. So colder as you go down, which makes sense, you're away from the sun's surface. Halocline is related to halogen, which is group 7, which includes chlorine, which is involved in salt. This is the change of salt with depth. Let's figure it out.